All right, in this chapter, we'll study the Newton's laws of motion. There are three laws, and we'll look at them. So, Newton's first law, Newton's second law involves force. We'll define mass, and then talk about Newton's second law. And we'll look at some special forces, the force of gravity, what do we mean by weight, what do we mean by normal force, and the tension. And tension in a string, for instance. So you'll encounter these words quite a bit. So we'll define them for you, and we'll look at Newton's third law. So Newton lived between 1642 and 1727, and in his Principia Mathematica in 1687, he proposed the laws of motion, and we still use them today. He also discovered gravity, he invented calculus, and made contributions to the theory of light and color. So he did, Mr. Newton did quite a bit of things. Even just one of those would have made him famous. So he was a smart man. All right, so let's look at Newton's first law. This was actually discovered by Galileo, but we call it Newton's first law. All right, so imagine an air hockey table, and you've all seen this. So you get a flow of air, and so the puck is sitting on a bed of air, on a layer of air. So that minimizes friction, and that's the whole idea. And you guys have experienced this. You shoot the puck, and the puck, once you shoot it, it maintains its constant velocity till it hits the side of the table or something like that. So in principle, if you had an infinitely long table, that puck would keep going forever, ignoring the little friction. So that's the statement of Newton's first law. When no forces act on an object, its acceleration is zero, meaning its velocity will remain constant. Yeah. And so it's stated as sometimes stated as if it's moving, it'll maintain its velocity, and if it's at rest, it'll remain at rest. The mass of an object is it's a measure of the resistance to change in its motion, but it tells you how much stuff there is in an object. Now, the reason we have this picture is the weight of this person might change depending on whether he's on Earth or on the moon, but his mass is the same. Mass is a scalar quantity, and the SI units for mass are kilograms. All right, the Newton's first law said if no forces act on an object, its velocity will remain constant. So if you apply a force on an object, its velocity will change. Okay. So in this diagram, these two people are pushing her, and in physics, we like to draw just the essentials. So she's represented by a point, this force is represented by that arrow, and that force is that. So a free body diagram represents the forces acting on the third scalar. So this is the relevant portion, and that's what we've drawn here. Now, as we said, forces change velocities. When forces act on objects, unbalanced forces, they'll change the velocity of an object. And forces are vectors, and they add like other vectors. So the total force, for instance, on this person is that, which is this force plus this force. That's the total force. All right, so here's the definition of the force. The force acting on an object of mass 1 kg is 1 Newton when its acceleration is 1 meters per second squared. So let's say you have a 1 kg object and you apply a force such that it accelerates at 1 meters per second square, then that force would be 1 Newton. All right, the superposition principle states the following. When several forces act on an object, the effect is the same as that of a single resultant force. Okay, so what that means is on this person, if there are multiple forces acting on her, the result of her motion would be the same whether it was these two forces or this single force acting on her. Okay, so that's the statement of the superposition principle. So in this example, on this mass, there's several forces acting. T, the tension in the string, the weight of the object, and the normal force that this block is exerting on it. So on this object, there are 3 forces acting on this object. On this object, there are 2 forces, the force of gravity and the tension in the string. This is the Golden Gate Bridge, and I just want to mention something here. So let's say all these suspension bridges are designed with the following principle in mind. It turns out that structures are much stronger under compressive forces. If you try and crush this versus pulling it apart, compressive forces, the structure is much stronger under compressive forces than stretching forces. So in a bridge like this, these cables stretch. Okay, so if you have a structure that has got, and the stretching force is called a tensile force. So if a structure in your experiences tensile force, you want the tensile force to be small, while larger forces that the structure has to bear should be compressive forces. So imagine that this bridge is supporting 100,000 pounds and there's 100 cables, then each cable only has to support 1,000 pounds stretching. And then ultimately, so these cables pull down, which pull down on this cable, which transmit it as a compressive force on this structure. So each of the cables in our example might feel 1,000 pound stretching force, but these guys will feel 50,000 pounds of compressive forces. Again, that's the idea behind these bridges. And you have the same idea here. These vehicles going there will push down on these structures, which will push down on them, which will ultimately push down on these structures, which bear the greatest load, and they're all compressive forces. All right, so here are the magnitudes of some forces. It turns out to stretch a DNA, the force needed is 10 to the minus 15 newtons. The force between the hydrogen and the proton and the electron in the hydrogen atom is about 10 to the minus 7 newtons. Okay, so roughly there. Okay. And the force on the Hoover Dam is 10 to the 11 newtons. Now the weight of a person is about 1,000 newtons. It's around 700 newtons. We'll call it 1,000 newtons. So that would mean that 10 to the 8 times 10 to the 3 is 10 to the 11 newtons. Yeah. So the force on the Hoover Dam of this water